Hello, I'm going to try to recreate the discussion that we had the other day that I forgot to hit record on. So this would be better, of course, if we had some live discussion with you guys. But there are some positive benefits to me screwing this up. Namely, I get actual copies of the images to work on. So hopefully that will be helpful to you. So anyway, so let's start here. So these are all from, I think it's problem, whatever. It's practice 6, I think. Reactions. Okay, so just go look in there and you'll find these problems. Okay, hopefully I made the font here big enough that you can read it. I'll go ahead and read it out loud on each one. A rod AB is hinged at A. Here's A. Okay, and attached at B to a cable BD. Here's my B, here's cable BD that supports the loads as shown in the figure. Given that D equals 200 millimeters, so 0, well, we'll leave it as 200 millimeters, because all those others are in millimeters. X equals 75 newtons, and Y equals 75 newtons, okay? And as you guys know, this is all algorithmic, so it'll give you a different answer each time for those things. Okay, what is it? Well, I forgot to copy what it wants. Okay, I'm going to guess it wants a free body diagram, and it's going to want to know, the reactions. Okay, so what's going on at D, what's going on at A. Okay, so, I don't have that written down, but I'm sure that's what we want to solve for. That is actually, in fact, what we're looking at here. So what we want to do here is we want a free body diagram. What I highly recommend when you think about free body diagrams is you think very strongly about what it is that you want. So in this case, we want AX and AY, and we want what's going on at D. Okay, so the nice thing about this is, so what we're going to do basically is I'm going to kind of I'm going to cut my system like here and here, because those things are going to tell me, because if I cut the world away from my system in such a way that those forces are at my cuts, then I know I'm going to get my cuts, okay? Because I'm going to get those forces, because we only care about the things that are acting on the external, basically they're crossing that boundary, okay? So if I draw my system and I cut it like this, okay? You're like, well, how does that work exactly? Okay, well, I guess technically, if we want to really get into it, we could say that, we've actually cut it in such a way that, let's do this, that, these forces are crossing it, okay, because those forces are external to the system. Okay, so what we're going to do here is I'm going to redraw this thing. Unfortunately, it won't be as pretty, but it will be a free body diagram, whereas what we have now is just a picture, right, or a diagram of some sort. But we like, oh no, give me a drawing tool, not a hand tool. Okay, here we go. Well, we're going to kind of try to go to scale more or less. It will make things a little bit easier to do things like that. Okay, so I'm just drawing the beam itself, and a little bit of that, sorry, you're hearing my rulers, I'm just kind of slapping my ruler down on my eye, this eye thing, whatever it's called, iPad or iPod, I can't ever really remember. Okay, so here's the rod itself, so here's point A, and here's point B, and we've got this thing coming off this way like this. Okay, and that's our force. Okay, so we can call that force whatever we want. I think pretty standard would be to call it BD or TBD. I'm just going to call it T because we don't have any other tensions, and it's just a nice, easy thing. Okay, we will also have forces here. Okay, so this is going to be A in the X direction. This will be A in the Y direction. And we know we've got both of those because this is a pin. So because it's a pin, like you can see that this beam, if it were free, like it could spin around that thing, no problem. But what it can't do is that point has to stay there. So if I tried to move it in the X direction, that nail or that bolt or whatever would prevent you from moving it in the X direction. It would also prevent you from moving it in the Y direction. It would not prevent you from twisting it. So there's no moment there. Okay, and then at these points, we've got these forces. Okay, 75 newtons. So what you want to do when you draw the free body diagram is you always want to think about what forces are acting on the external of this thing. Okay, of your system. And all those are the externals. The only internal forces that you ever have to worry about are what we call body forces. And in statics, that's really just going to be gravity. This beam, of course, has gravity, but we have decided to neglect it by whoever wrote the problem, because they didn't mention it at all. So So we're just not gonna stress about that. Okay, other things that might end up being helpful, and we might as well just go ahead and get them right now. I think hopefully you're getting to a point where you're starting to see that, this is a good idea. So, obviously I didn't do a perfect job of drawing T here, but we might want this angle right here with the horizontal, because we don't really like to work with T on an angle. We like to work on it in an X or a Y fashion. So, I'm going to go ahead and get that angle right here, right? And I don't know what we'll call it. We'll just call it theta. And we'll do the standard, like, here's my triangle. Let's see here, the tangent of that angle, okay, equals the opposite, which is 100 millimeters, over the adjacent, which is also 100 millimeters. So inverse tangent of 1, it's going to tell me this is 45 degrees, okay, which should have been expected. Okay, so that just kind of helps out a little bit. Okay, so I didn't write down what we're going to solve for here, but we're going to go ahead and solve for everything. Okay, so we're going to solve for the reactions. We want to know what's going on at D. The nice thing is we know what's going on at D. Basically, it's pulling on this whole thing with whatever T is, okay? Or the whole thing is pulling on T in that direction, okay? AX and AY, I don't know what they are. I always assume they're positive if I don't know anything about them. Okay. Obviously, T I chose in the positive Y direction, but the negative X direction, because it's a cable, and cables can only pull. So if I end up getting a negative number there, then either there's something wrong with the problem, or more likely I'm in an error, right? So let's hope that doesn't happen. Okay. So in every problem in statics in 2D, well, in every problem, these are your equations. Okay. The sum of the forces equals 0. And the sum of the moments equals 0. And I put that arrow on there because really this is the sum of forces in the X, sum of forces in the Y, and sum of forces in the Z equals 0. For the moments, it's the same thing. Sum of the moments in the X equals 0, sum of the moments in the Y equals 0, sum of the moments in the Z equals 0. But in 2D, what's nice is we only have, this splits out twice, and this only splits out once. Okay, so we don't even really need it to, it doesn't really split out. It just, the other ones go away. So in this case, it's the sum of the moments in the Z direction equals 0. Now, standard is to really ignore the Z in 2D. But if, like, this is the X direction, okay, so that's my fingers. Okay, we're doing right-hand rule here. And this is the Y direction. That's my palm. Okay, then the Z direction, the Z direction, is my thumb, which is right here, and it's coming straight out at my forehead. It's facing right at me. And what does that mean if we have a positive moment? Well, it means that my fingers are going to curl around this way. Okay, so that's a positive Z, is the way that my fingers go. Okay, or we usually just, a lot of times, especially in 2D, we just say counterclockwise. Okay, but it's true that that would change if for some silly reason you decided you wanted Y down here. Okay, so I don't recommend putting Y down there. Okay, X and Y should be a right angle such that your thumb ends up going upwards, or else everything gets wonky, right? So there's no reason to go wonky. Okay, so in the X direction, in the forces, though, we're going to do sum of forces in the X equals 0, sum of the forces in the Y equals 0, and the sum of the moments in the Z equals 0. I left a little space right here because we have to choose where we want the moment. And that is an important part, right? Because I could put my thumb right here, I could put my thumb right here, I could put my thumb right here, I could put my thumb right here. I could put it in any random point I want, and it doesn't even have to be on the beam. It can be anywhere at all. Okay, and we'll, in a second, we'll talk about how to do that, right? But right now, let's just do the forces, because usually the forces are the easiest thing, but they may or may not help me. Okay, so let's go ahead and do it. And right now we're being a little unscientific here. Okay, because if you want if you want all of the reactions, sometimes it's going to require all of the equations. In fact, it seems highly likely here, and I'll tell you how I know that. It's because we have 3 unknowns: AY, AX, and T. We have 3 unknowns. We have 3 equations: 1, 2, 3. That pretty much means we're going to need all 3. Okay, if we had 4 unknowns and 3 equations, we couldn't solve it, right? You need to have the same number of unknowns as equations. Okay, so in this case, we're going to need all 3. So we don't really need to be all that scientific here. We just know we're going to need them. So here's the X equations, the X forces. We've got AX. Let's see, AY is vertical, 75 newtons is down, 75 newtons is down. And then we've got this t, so we've got minus t, and we want the component of that is in the x direction. So that's going to be t cosine 45 degrees equals 0. Okay, notice, let's see, so those are all the x forces. And notice we've got, let's see, this equation has two unknowns. We can't solve it, right? It's two unknowns in one equation. We can't solve it. By the way, here's tx and here's ty for those of you who are still kind of working on the trig here. And you can kind of do that on your own. And then, okay, sum of forces in a y. Well, I've got an ay is going upwards, so it's a positive. I've got 75 going down. Okay, that's this 75, and then this 75 is also going down. And then I've got the ty going up. So I'm going to go ahead and add t sine theta equals 0. Okay, notice this equation also has two unknowns, ay and t, so we can't solve this one either. Combined, these two have three unknowns, and we can't solve three unknowns with two equations, right? So I'm going to go ahead and simplify this one because it's a little bit ugly right now, minus 100. And let's do it like this, actually. I like it like this because it just kind of makes a little bit more sense to me. Plus ty sine, well, we won't use theta, we'll use the 45 degrees. Equals 150 newtons. So I just brought the 150 over. So this makes a lot of sense to me because this tells me that basically stuff is pulling down with 150. So stuff that's pulling up has to pull up with 152, right? They have to equal, okay? If stuff was pulling up harder than stuff was pulling down, this thing would accelerate upwards, right? So it was pretty straightforward, I think. And, you know, we could do the same sort of thing over here. Ay equals t cosine 45. Okay, and that means whatever ay is, it's pushing against that tension. Okay, I mean, you can imagine if you went up here, you were like right here, and you decided to pull harder on the rope. You can imagine that ay is going to have to respond by pushing back a little harder, right? And if that bolt can't hold it, well, then it's going to bust. But you know, you're an engineer, so we're going to fix all that pretty soon. Okay, I'm going to do the sum of the moments. I kind of crammed it in there right there, so I'm going to go ahead and redo it here. And we're going to think about where we want to take that moment. Okay, where do we want to take that moment? And I'll tell you, in my opinion, there is a correct answer here. Okay, I could take it. So, and here I'm going to demonstrate by picking this point right here. If I pick this point right here, then what happens is that 75 Newton, it's going right through the middle of that, you know, what do we call the center of the moment, or the fulcrum would probably be the best term for it. And so the 75 Newton, because it's going right through that fulcrum, it has no moment arm. So it's going to offer no moment. So that means that when doing this calculation, that 75 gets multiplied times a 0 and it goes away. However, this AX counts because it's going to end up like right here, so that's its moment arm. This AY counts, so if I slide it down, let's see, so we're sliding that one over, let's slide this one down, and it's got a moment arm right here, right? This 75 Newton, it's got a moment arm. And this T, if I wanted to just use basic regular T, like it would have a moment arm way up here, and that's, of course, annoying, so we would never do that because that's just a lot more work than we want to. So instead we do Tx and Ty, so Ty would go up here, have a moment arm right here, and Tx would go like this, and have a moment arm like that, right? And that's a lot of forces, right? Now notice that equation that we would come up with would have Ax in it, it would have Ay in it, and it would have T in it. Actually, it would have Tx and Ty in it, but I guess it would have T in it because we would just put a cosine and a sine in there. But that is not ideal, right? We don't want to have to deal with three unknowns in the moment equation. We can do it, and then we'd have to plug these other two equations in to it, but I don't want to do that, right? I want to make my life easy. So what I'm going to do to make my life easy is I'm going to pick this point right here. Because if I pick this point, then what happens? Well, Ax and Ay go away. So I'm going to do this in blue because I haven't used any blue yet. So this is going to be our point right here. Okay, and by choosing A, I make my life easy because I get a moment arm of 0 for Ax and Ay because they go right through the middle of it. Okay, so now let's see. So let's start working on this. Okay, so the first thing I got to do is I got to start with this 75 Newton right here, 75 Newtons. And I need to remember that positive z is going this way. So we can put a little positive z right there. That's 75 newtons if I slide it on up until it's, perpendicular. There it is. Okay, and hopefully you can see this is the perpendicular distance right here, or the moment arm is 100 millimeters. Let's use 0.1 meters because I like standard units if I can. And then we need a sign for that. Okay, and notice that that's going to cause this thing to spin that way, which is the opposite the direction of positive, so we'll call that negative. This 75 we would slide up to here. Okay, and notice its moment arm is from here all the way to here. Okay, so that's 200, so 75 newtons times 0.2 meters. Okay, and again, it's spinning the same direction, so we'll put a negative sign right there. Okay, now we've got a tx and a ty. This ty is right here. Okay, I'm going to slide it on up until it's perpendicular, right there. Okay, notice its total distance is all this business. Okay, so that's 0.3. Okay, so that's going to be ty, so that's t sine of 45. Okay, times its moment arm, which is going to be 0.3 meters. Okay, and note that it wants things to spin in a positive direction, so it gets a plus. Okay, now I've got tx, which is going to go this way, right? So I'm going to put it about right here, and its perpendicular distance is right there. And it's not on this picture, but up here it says it's 100 meters. So we'll go ahead and use that. Okay, so that's what's that, tx. So that's going to be t cosine 45 degrees. Okay, times 0.1 meters equals 0. And we need a sign for that one. And it looks like that one is going to go negative, the opposite of that z. Okay, so there you go. So that equation is one equation, one unknown, t. So we can solve that one, which is awfully nice, right? So let's go ahead and do so. I mean, at this point, this is just like an algebra assignment. So I'm going to kind of pause and do some work here. And so we get some kind of number like 159.10 newtons. Okay, so that's the tension. Okay, and so these two terms combined here, and these two terms combined here. Okay, so that's how we do it. Okay, so that's the t. And then the cool thing about this is by cleverly choosing my moment where I want, I'm able to solve t, and then I come back over here, and these are like easy to solve, right? Or maybe not easy, but they're plug and chug. By the way, this should have been just a t, right? Because we handled the y by giving the angle on it. Okay, so ax equals t, which is 159.10 newtons, times the cosine of 45. Okay, so ax equals, let's see here, times cosine 45 is 112.50 newtons. And notice that that's positive, so that means we assumed the correct direction, which is the only way that made sense because the rope was pulling to the left, so the whatever was at A was going to have to push back to the right, okay? AY, on the other hand, let's see how that one works out. So AY plus 159.10. Let's see. Sine 45 degrees equals 150 newtons. Well, we know what this quantity is. It's 112.50. So AY is going to equal, is that 37.500 newtons? We probably don't even know it really to that precision. So we can say that ultimately, let's see, T equals 159 newtons, AX equals 113 newtons, and AY equals 37.5 newtons. Okay, and it looks like we assumed the correct direction on all of these because they all came out positive. Okay, obviously, or maybe not obviously, but if the question asked for the magnitude of A, you could square you would square this and add it to the square of that, and then take the square root, and then you need to get the angle. Okay, but I'm not sure what this question asked, but I think, this is the gist of what we were working on when I signed it. It's amazing how messy these things get. All right, anyway, so let's go over here. Okay, so this obviously gives a slightly different question than what we saw when I did this live. Well, just because this number is different. I think it was 17 pounds when I did it live. Anyway, sorry, you guys are hearing the creaking of my chair. I really need to get a non-creaky chair. Okay, so 23-pound square plate is supported by 3 vertical wires. Okay, so what we're going to do is we're going to draw a free body diagram, determine the tension in each wire, and determine the value of A for which the tension in each wire, blah, blah, blah. Okay, so what we're going to do is I'm going to cut this free body diagram. So I'm just going to cut it like just where those cables come in, right? So, I don't know if I can really draw what I'm slicing, but I'm just drawing the plate itself. Okay, so here's the plate itself, to the extent that, I can draw, which is, not nearly as good, or not nearly as well, as this computer. Okay, so now we've got forces, right? We used to have a rope there, but now we've got a force, A. I could call it AY, but I'm not going to because the A only goes in one direction. So here's B, and here's C. Now, any other forces? Okay, so when I isolated that block, I had to think about where was I removing it from the world? So when I remove it from the rest of the world, I need to replace the rest of the world with forces. So the only place where this thing was touching the rest of the world with those 3 cables. However, I need to think about, so those are all of my surface forces. However, there is a body force in this case, and that is the weight. So we need a weight, which is going to come down right through what we will learn shortly is called the centroid. Right now, just think about it as the center. Okay, the centroid and the center are very similar words, and there's good reason for that, but they're not exactly the same thing. Okay, so there we go. So that's our free body diagram. Okay, so we want to figure out the tension in each wire. So I want A, I want B, I want C. Okay, you'll notice that B and C are symmetric, so we should totally expect that they're going to give us the same number. Okay, and when we solved it, that does end up being the case, but we'll go ahead and just work it as if we don't know that. And then, we'll see what happens. Okay, so again, we're now in 3D, so we have equations. Sum of the forces equals 0, that's 3 equations. And then the sum of the moments equals 0, that's also 3 equations. Yachi-machi, right? So we've got a lot of yachi-machi going on here. However, we can probably get rid of a few of these, and let's think about this. Let's see, the sum of the forces in the x equals 0, sum of the forces in the y equals 0, sum of the forces in the z equals 0. Sum of the moments in the x equals 0, sum of the moments in the y equals 0. Sum of the moments in the z equals 0. Okay, so I've just written these out so that these are no longer functional equations because we're not going to use those, right? Because I've split them out. Okay, so if we look at this, let's see, this is the x direction. Do we have any forces in the x direction that we might want to sum to equal 0? Doesn't seem like it, right? So let's get rid of this one. Let's not use this one. Okay, what about the y direction? So here's the y direction. Do we have any forces in the y direction? No, we don't have any forces in the y direction. So let's not even waste our time with it. Okay, what about the z direction? Well, the z direction, and you could have figured this out before you took this class, those 3 ropes are going to be pulling combined with to equal the weight. So I could say, well, okay, let's do this one. A plus B plus C minus W equals 0. Okay, those are all the forces. They're all in the z. Oh, no, wait, that's the y direction. No, dadgummit. Okay, you see how you are? Who am I blaming? I'm going to blame my dog. Okay, so we have nothing in the z direction. This is a z, right? This is the y. Sorry, old habit from fluid mechanics, where up is often z, okay? Depends on who teaches it. Anyway, so sum of the forces in the y equals 0, a plus b plus c equals minus the weight equals 0. So as you probably already knew, a plus b plus c, we're going to have to be equal to the weight. Okay, you've got a 22-pound weight. Each of those 3 cables is going to have to you know. Now, ideally, you would want them all, like, you know, you'd want to situate these so that if they're all the same cable, they're all going to hold the same weight, so then there's no weak link. Okay, and that's the second part of this problem. Determine the value for A, so if we adjust where these cables are, we can figure out where we have the same tension in all three. Okay, but for the first part, though, we're going to assume that this distance right here is 10 inches. All right, so this one right here is 10 inches. This weight is acting right in the middle, so if this whole thing is 30 centimeters, or 30 inches, excuse me, then that weight is kind of happening at, wait for it, you know, 15 inches, okay? And so, and from all sides, right? So I could do it this way as well. So it's going 15 over here. Okay, so for now, you know, just trust me, it's happening at the center. On a test or something, we would have to, well, we're going to teach you how to do centroids soon. So anyway, so that's the idea. Okay, so now we think about moments. Okay, I'm going to look at the original drawing because my free body diagram really is ugly. So let's turn this into a free body diagram. We've got a weight going down right here. Okay, so now I want to think about the moments, and the moments in the x direction. So what does that mean, the moment in the x direction? Well, what it means is something is causing things to spin around. I'm going to take all of my moments at A, just because it makes things easier to discuss. I mean, you could do it at different places, but it's nice to do it all at A because I know I'm never going to have to deal with this force A in my moment equations. Okay. Now, I mean, I could have done it at C, I could have done it at B, but A is, in fact, right on the axis. So what I'm thinking about here, so first of all, let's take your thumb and point it in the x direction mentally. And what are your fingers doing? Well, your fingers should be curling over the top here if your thumb is going this way. That's a positive x moment. Are any of these forces trying to create either a positive or a negative x moment? Are any of them trying to make it spin around that axis, you know, the plate? And hopefully, you know, what I'm hoping that you can see right now is that C is causing it to want to spin that way around that plate. Okay, like if there were a hinge, you know, if there were a row of hinges at X, you know. And that B is also causing it to spin that way, or want to spin that way. W is causing it, you know, the weight is making it want to spin the opposite way. Okay, so those are your forces that are causing you know, a moment. Now, at A, it's going right through that hinge, so it's not doing anything. So we don't have to worry about it. Okay? So let's go over here and let's do that equation for the x direction. Okay, some of the moments in the x direction. Let's see. Maybe we got to do it over here. I really kind of, you know, box myself in here. Some of the moments in the x. And I'm going to take them around the point A equals 0. Okay, so let's see. We've got three forces, B, weight, and C. So I'll start with, I'm just going to kind of go from left to right. So here's B. Okay, how far away, what's its perpendicular distance, its moment arm, from X? Well, it looks like it's like that. Okay, so that's going to be, what, 30 inches? Nope, nope, don't do that. Nope, what are you doing? Thank you. Okay, B times 30 inches. Can you give me my pen back? Thank you. 30 inches. Okay, now we have to think about whether or not that's positive or negative, and we're going to refer to this right here. Okay, and it is going the opposite of that positive, so that's a negative. Okay, now we'll go in order. We'll do weight. Weight is going in the same direction as that, is this curl here. So we'll do plus the weight times its distance, which is from here to here, which is half of that 30, so that's 15 inches. Okay. And then we've got this C, which is going this way. And so we're going to say that's a negative C. And it's actually, it is 10 inches because this problem says, you know, the A part says to make it 10 inches. I'm going to leave it as A for now so that I can use it for part B, right? Because I know in part B we're going to solve for A. So I'm just going to leave it like that for now. Okay, so that's just some of the moments in the x direction. Now note that, okay, so that's cool. Sweet, we did that one. Now what about in the y direction? is any of these forces causing this thing to spin around this axis, which is kind of hidden back here. Okay, so what I'm asking for is you put your thumb up and you're saying, well, which ones of these are making this thing spin that way? Okay, so and hopefully you can see that this weight is pulling parallel to that. So it's not making that thing spin like a top at all. It's just pulling it downwards. Okay, these are pulling it upwards. Okay, but they're not causing it to spin circularly around this frame, or excuse me, around this axis, right? Like that. It's just not what's happening. So this equation is useless to us. Okay, because there are no forces there. Okay, now the z direction, on the other hand, so if I go in the z direction, so here's the z direction, and hopefully you can see that if that is a hinge on the side of this, every now and then you can hear the rumble of the Roomba in the background, okay, is that if that is the hinge, right, so this is the positive z direction, what does that mean? That means if I put my thumb in the z direction, looks like my fingers are going to be curling over the top like this, so that's a positive z moment. Okay, and hopefully you can see that, let's see here, B is going to be going positive, C is going to be going positive, and W is going to be going negative, okay, relative to that axis. Okay, so here we go, the sum of the moments in the z direction around point A, because we're still kind of using this point right here, equals 0. I mean, really, we're doing an axis, but the axis has to go through somewhere. Okay, so then let's see, can we get those distances? Well, let's see here. We got B, which we decided is positive, and it's times A, plus the weight, which we decided, so here's the B distance right here, and then the weight, which is this distance. The weight times, it looks like 15 inches, okay, because it's halfway out there. Now it's going negative, so we're going to go ahead and erase that positive sign and put a negative there. And then the C, okay, its distance is all the way from here to here, right? So its perpendicular distance, or moment arm, is 30 inches, and it's positive, plus C times 30 inches equals 0. Okay, so those are our equations. I should note, I kind of screwed up a little bit here. Not really screwed up, but these weights, we know the weight is 23 pounds, so I'm going to go ahead and put that in there. If it'll, select. Tends to get angry once you get about 20 minutes of video. Come on, buddy, you can do it. Come on, 23. 23 pounds. 23 pounds. Okay. So what we want to note here is this one has, well, let's see. Let's go over here. We can do the same here. 23 pounds. Oh, it doesn't like switching back. That's the problem. Okay, you just have to bear with me. So what we're going to note is that in the equations on the left, we are 2 equations, 2 unknowns. Okay, so this is 23 pounds. I don't know how I got red there, but that's fine. So these equations, this has B and C. This one has B and C. So I can solve one for B or C and plug it into the other. Okay, it's that's pretty straightforward. In high school we called this the Simus solve. Okay, so I'm going to go ahead and do the bottom one. B times A equals 23 times 15. Quick, in your head, what is that? I don't know. 23 times 15 is 345. So 345 pound inches. So let's see, pound inches. Maybe, I don't know if that's legal. Anyway, you know what I mean. Minus C times 30 inches. Okay, so B equals 345 pound inches minus C times 30 inches divided by A. Okay, so that's B. Okay, I'm going to plug that back into this equation up here. Okay, I mean, I'm going to do it down here, but, I'm just kind of showing you. So I could say, so instead of, I'm going to have negative, so instead of B, I'm going to have 345 pound inches minus C over 30 inches divided by A. Maybe it's a good time to plug in the, that should be inches. Maybe it's a good time to plug in the old, the old A is 10 inches. That's probably about time. We'll do that in a second. Okay, plus 23 times 15, which we decided was 345 pound inches. Okay, and some of you guys may have noticed, pound inches, pound feet. What is that? Well, that's usually a torque, right? And a torque is nothing other than just a fancy word for a moment. Minus C times A equals 0. Okay, now notice by doing that, we have an equation with one unknown, which is C. Okay, so I think at this point, it'd be a good time to plug in that 10 inches for A. So what I'm going to do is, just for, space saving and time saving and all that other stuff, well, I wanted that in black. Do C, and then I'm going to plug in the 10 inches, okay, because we know that this is a given in this problem, 10 inches, 10 inches. Okay, and so that'll kind of clean this up an awful lot. It will also basically solve the problem for us, okay, because we can go down here and I could say, well, 345 divided by 10 inches, well, that's 34.5, and the inches cancel, and I'm left with pounds minus, or plus, I guess, because we have to distribute here. 3C, all of this is being multiplied by 30 inches, plus 345 pound inches minus C times 10 inches equals 0. What's the quick way to do this? I don't particularly like this very much now, do I? Do you like it? I do not. Well, one thing we can do is we can divide everything by 10 inches. Yes, let's do that. We're going to divide everything by 10 inches. So this becomes, let's see, so this one becomes 34.5 times 3. 34.5 times 3 is 103.5 pounds. That's a negative. Plus 9C. Plus, we divide this one, 34.5 pounds minus C equals 0. So what's that? 8C equals 103.5 minus 34.5. So we'll go up here and we could solve that and say that C, so divide that number by 8. 8.625. Okay, pounds, I guess? Yes, pounds. Okay. And if we plug that right back in here, we will get B. Okay, and if we put in a 10 for A, I don't even really need to do this because we know it's symmetric, so we know the answer will work out. But let's go ahead and do it. So let's multiply that number by 8.625 by 30. Okay, make it negative. Negative 1, multiply by the negative 1. Add the 345. Okay, and divide by 10. Okay, and B is 8.625 pounds. Okay, and that's awfully reassuring because from symmetry, we knew that these two things were going to be the same. And then what I can do is I can plug both of them into this equation, right? And I can say A plus 8.625 plus 8.625 equals 23. And so if I plug all that in, and I get A equals 23 minus 8.625 minus 8.625. Okay, so take that answer in my calculator, multiply times 2, make it negative, and add 23. And we'll get that A is 5.75 pounds. Okay, so that's how we solve it. A little ugly, lots of arrows, things. All right, so if we wanted to solve the B part, determine the value for A for which the tension in each wire is this number. Well, notice that number means, like if I go down to this equation right here, well, that equation becomes what, 7 2/3? Yeah, 7 2/3. 7 2/3 pounds plus 7 2/3 pounds plus 7 2/3 pounds equals 23 pounds. Check. Okay. Useless. Okay. No help to us. Okay. On the other hand, I can go over here and, you know, like I can pick any equation that I want. So this one looks tempting because it's got a nice big box on it, but it's a little bit kind of ugly to work with. So instead, I'm going to work with either this one or this one. It's kind of up to you. They're basically the same equation with just B and C kind of swapped position with different signs. But let's just go ahead and use this one. And what I'm going to do is I'm going to make use of the fact that I have different unknowns. Okay, and this is why it's always best to work with variables. I just smacked my lips. I hate when people smack lips on recordings. I apologize. So anyway, so I'm going to bring this back down here. And so I've got B times A minus 23 pounds times 15 inches plus C times 30 inches equals 0. And what I'm going to do is I'm going to use the... Come on now. Can you just move for me? Can you slide? Okay, I'll just do it right here. Okay, B is going to be 7 2/3. Okay, pounds times A minus 23 times 15, which we decided was 345 pound inches, plus C, which I know is 7 2/3 pounds times 30 inches equals 0. All right? Okay, so we just solve for A. Okay, so 7 2/3. I don't know how this calculator does 7 2/3. Here we go. 7 2/3. Oh, it hates it. It hates it. Anyway, 7 plus, clear, you punk. Okay, 7, 7 plus 2 divided by 3 works. Okay, times 30. You know, this is really dumb. Why am I making this so hard on myself? Anyway, 230, okay, minus 345 equals whatever that is. Some negative number. We bring it over to the other side, so we multiply by the -1, and then we're going to divide by 7 2/3. Divided by 7 plus 2 divided by 3 equals 15. So A equals 15. And the units are going to be inches, because we got pound inches in all of these, so inches. Okay. It's actually kind of interesting. Very surprising, actually. Almost makes me think there's an error somewhere. Anyway, yeah, whatever. Okay. The method is correct one way or the other. So, you know, maybe I made an error, but the method is correct. Okay, so that's what I want you to get out of this. Get the method right. Okay, if there's an error somewhere, it's okay. All right, so the last one. This is a bit of a doozy. Let me go ahead and erase this stuff that's in my way. Okay, if you are in my way, I will erase you. Sounds like a good Schwarzenegger movie. All right. All right, a 7-foot boom is held by a ball and socket at A, and by 2 cables, E, B, F, and DC. Okay, so what's interesting here, one of the interesting things about this problem is that this cable is all one cable, which means the tension to EB and the tension to BF are the same, which is probably why I'll probably just end up calling it T, probably. I haven't really decided yet. It passes around a frictionless pulley at B, which is just their way of saying don't worry about the pulley. Okay, consider P is 380 pounds. P is 380 pounds. Okay, draw the free body diagram and determine the tension in each cable. We got 2 cables. All right, so I'm actually going to solve this, at least the moments in this case, I'm going to solve them 2 different ways. There's the way that I like to do it, and then there's kind of the way that McGraw-Hill likes to do it, and sometimes Jeff Hansen will do it this way. Usually in 3D he does it this way, so we're going to do both. All right, so free body diagram. I may not draw the free body diagram because this is just too busy for me to draw a free body diagram. So here's what I'm going to do. I'm going to draw the forces in red, okay? And what I want you to do is ignore the rest of the picture except the boom, okay, the 7-foot boom. So we've got a force here going up. That's AY. Okay, we've got a force, because this is a ball and socket joint. Okay, so that means it basically will not support a moment, but it will support forces. So you cannot move it out of that spot, but you could wiggle it around. You could like spin it around if you wanted to. So this will be AZ, AZ, and this will be AX, AX. Okay. Now I've got a force EB, which is just going to be a capital T. And I've got a force going this way, which is also just going to be a capital T. Okay, I'm not going to call them different things because I know they're the same, because they're going through a frictionless pulley. Okay, I've got a force here in P. Okay, and I've got a force right here. Okay, and I know these are pulling, right? Because, so I'll go ahead and call that TCD, because they're cables. That's what cables do. Okay, so we're going to call that the free body diagram, just because if I were to draw a free body diagram of this, I would make a mess of it. So at least on this medium. If I was on a pad of paper and I had a ruler, I could do it. Anyway, and hopefully you can too. So we're not concerned at all about what's going on here, here, here. We care about where their location, or E. We care about where they're located, because that tells us, that helps us figure out things about the forces, but we don't really care about, you know, like we're not, there's no, as far as we're concerned, that's the outside world. We don't care about that, okay? We also don't care about what's going on inside the beam, okay? Like I don't really need to know how, you know, a point, oh, dadgummit, give me a, okay. I don't care about a point right here or a point right here, how they're affecting each other. They are pushing on each other, certainly, if they're next to each other, but we don't care, because that's internal. So we're only worried about things that are pushing on our system, and the system in this case is the beam, or the boom, okay? So now, we're in 3D, so we've got equations. Sum of the moments, look at you guys. I didn't know you cared. Okay, sum of the forces equals 0, that's 3 equations. Sum of the moments equals 0, that's 3 equations. Whew, 6 equations. How many unknowns do we have? Well, it looks like unknowns, we've got AX, AY, AZ, T, and TCD. Well, that's nice. We've only got 5 unknowns. 5 unknowns means we won't need all 6 equations. But we're going to have to be a little clever about which ones we use. So how do we do this? Maybe the first thing we want to do is we want to define some of these forces. How's that sound to you? Does that sound good, like a good idea? Let's define some of these forces. Let's start with the T, the force T. And I want to know the force of T on the boom, because again, we don't care about what it is out in the outside world. We only care about what it is. But we kind of got 2 parts of this. So I got this one T right here, okay, which I'll go ahead and define that one by saying, well, that equals, well, okay, I'm gonna put this little thing here. Well, what directions is it acting in? Okay, and let's see, do I have a color that would be good for directions? Let's do blue for directions. And let's see, so it is going in the negative x direction, right? So I'm going to go ahead and say negative t in the x direction. And let's see, let's not do it like that, okay? It's going to be negative in the x direction. Now we need that little fancy lambda, what do they call it? Okay, yeah, what's the lambda, you know what I'm talking about. Okay, let's get the lambda first. Okay, let's get the direction for t first. Okay, so the lambda for t, right? The unit vector for t. Okay, well, in the x direction, it's negative. Okay, it goes that direction 3 feet. It goes from here to here, right? So that's 3 feet. And the magnitude of that thing is what? 3 feet going in the x direction, and it looks like 3 feet in the y direction. So that angle is pretty clear. It's 45. But we'll go ahead and we'll do this officially. So 3 feet squared plus 3 feet squared, like that, right? Okay, so that's in the x direction. Okay, it's also going in the y direction. It looks like it's going in a positive y direction because it's heading up this way. So we'll say plus, and that's a 3 feet, divided by the square root of 3 feet squared plus 3 feet squared. Okay, and that's in the y direction, so that'll get a j. Okay, we've got another maybe we'll call this like, T, I don't know what to call this one. We'll call this TEB, I guess, or TE. How's that? Let's call it TE, and we'll call this one TF, okay? Because we need some way to distinguish the fact that these are not, I mean, the magnitudes are the same, but the directions are different. Okay, TE. Okay, so then we got lambda TF, yes, equals. Okay, that one, it looks like it's in the XZ plane. So let's go ahead and we'll, let's see. So in the X direction, it's going negative. Looks like it goes 3 feet in the negative. So we'll go negative 3 feet in the X direction, I. Okay, and then it goes in the negative Z direction going this way, right? Minus 6 feet in the Z direction. Okay, so that's a K. Okay, and so we need the magnitude on the bottom. So it's going to be 3 feet squared plus 6 feet squared, and this one will be 3 feet squared plus 6 feet squared square root. Okay, so these things, I guess we should go ahead and do TCD while we're here. So we'll go ahead and go with lambda of TCD equals, let's see here, TCD is going in, everything's going in the negative X direction these days. Negative, it goes, looks like it goes 7 feet. Okay, and it doesn't go in the Y direction, but it does go in the positive Z direction. So plus, and this will have a K on it. Looks like it goes 4 feet. 4 feet. Okay, so we've got 7 squared over 4, 7 and 4 squared on the bottom. So 7 feet squared plus 4 feet squared. 7 feet squared plus 4 feet squared for the magnitude, just like that. Okay, so so these lambdas, they are what they are, right? So let's see, where's my calculator? Okay, I'm going to pause this while I punch this in because I don't think anybody wants to listen to this. This method is a little bit less thinking, but it's also a little bit more time consuming. I think it's probably a little bit more foolproof though, so there's that. So this will be M-A-W. Okay, so we'll put W's in here and W's in there. Go I, J, K, and this one's going to be really sparse. Okay, so let's see here, 70070 feet, and negative 380 pounds, 000, negative 380 pounds. Okay, so let's see here. That one goes away. Well, let's get back to black. Okay, this one is a 0. This one is not a 0. Okay, that's in the K direction. We get negative 380 times 7. Negative 380. Okay, negative 380 times. Why are you insisting on doing this? Negative 2660, so that's going to be in the K direction, negative 2660. Pound feet, so foot pounds. Okay, and that's a negative sign because of that right there. And then we go this way, we got a 0, we got a 0, and we got a 0. Okay, so 0, 0i plus 0j. All right. So then what you can do from here, you've got all your moments in one place. So you can say the sum of the moments equals 0, and you can do all of them. Okay? And really the simple thing here to do is to note, well, we're just going to note a few things here. Notice this. Okay? Remember up here? Okay, if we go all the way back, look, we knew that this was 0, right? Okay? What about this? Okay, this equation right here. Okay, so if I add those up and I know that the sum of the moments equals 0, all this is going to be 0, which means these two things, 2.6833 TJ plus, so positive, minus 3.4730 TCD. So if we go up here, that's these numbers right here. If I multiply those two, let's see, let's just do that real quick. 7 times 0.49614. It's going to give me, this is a 3.4730, negative 3.4730, which is the same coefficient we have on CD down here. Okay, notice this right here, boom. Okay, this 2.6, that positive 2.6833, that's this right here, 3 times that. Okay, that'll be the coefficient there. Okay, so in other words, we did all that work and we get this exact same equation right here. I can say that this plus this equals 0. Okay, notice this last equation right here, 2.1213. That's this right here. Okay, 3 times, we can go ahead and plug it in if we want. And we get 2.1213. Okay, and then we got this negative 380 times 7. Negative 380 times 7 is this number right here. So we can add all these things up, and they add up to 0. Okay, so basically this is another way to get the exact same equations that we did over here. Okay, so it's the same method. It's just one, you're letting the math do the thinking for you. Yeah, I think this is a little bit more like reliable, but it's also a little bit slower. So it's just kind of up to you, whatever you want to do. Okay, so this is a really long thing. I think it was when I did it live as well. It was about this long. So you know, watch it in steps. Hopefully I'll remember after I upload it to put some chapters on there, so it'll be a little bit easier. Anyway, I hope this is helpful, and hopefully the recording isn't all messed up. So take care of yourselves, and let me know if I can help with anything moving forward. All right, goodbye.